Here is a combined summary of the two pages. The point defect kinetics equations, based on rate theory, describe the concentration of radiation-induced point defects in materials under irradiation. However, the parametric uncertainty in the rate constants of competing physical processes, such as recombination and loss to sinks, can lead to a large uncertainty in predicting the time-evolving point defect concentrations. To address this issue, the authors employ perturbation theory to derive up to the third-order correction to the solution of point defect kinetics equations. This new set of equations enables a full description of continuously changing rate constants and can accurately predict the solution up to 50% deviation in these rate constants. The point defect kinetics equations, mathematically represented as equation 1, describe the change in defect concentration due to several competing processes, including direct defect production from irradiation, vacancy interstitial recombination, and defect loss to sinks such as dislocations and grain boundaries. The values of the rate constants, such as defect production rate, vacancy interstitial recombination rate constant, and vacancy sink and interstitials ink reaction rate constants, are significant in solving the concentrations. Uncertainty in the rate parameters arises from lower length scale computational methods, such as density functional theory and molecular dynamics, used to determine fundamental quantities like interaction strength and diffusion energy barriers. To perform parametric sensitivity analysis and uncertainty quantification, the authors utilize perturbation theory. By considering a perturbation to an input parameter k in the form of k right-pointing arrow k, 1 plus epsilon, the solution can be expressed as a perturbative expansion, as shown in equation 3. The correction terms, such as C1, V, C1, I, C2, V, and C2, I, can be found by substituting the perturbed equation into equation 1 and matching the coefficients of the perturbation epsilon. The equations needed to find results up to the third order are listed, including those for perturbation on K0, as shown in equations 4 to 6. These analyses can be combined to yield a multi-parameter uncertainty quantification considering the joint distribution of the rate parameters. Here is a combined summary of pages 3 and 4 of the research paper. The authors conduct sensitivity analysis and uncertainty quantification on point defect kinetics equations using perturbation analysis. Specifically, they investigate the effects of perturbations on 4 input parameters: kVs, kis, cs, and kiv. The equations governing the changes due to these perturbations are derived and presented in equations 718. For kVs, the equations to solve for the change are given in equation 79, where the change in concentration C1, V, C2, V, and C3, V is expressed as a function of the perturbation in kVs. Similarly, the equations for kis are presented in equations 10-12. With the last term in each equation replaced by kis changes. The equations for Cs are given in equations 13-15, which are identical to those of kVs and kis except for the last term being the sum of those of kVs and kis. Finally, the equations for kiv are presented in equations 16-18, where the change in concentration C1, V, C2, V, and C3, V is expressed as a function of the perturbation in kiv. The authors note that the corresponding equations for each input parameter are identical except for the last term, which is replaced accordingly. The results of these perturbation analyses can be used to predict the change in results on fine grids of perturbations. By solving a few more equations, the deviation from the unperturbed solution can be calculated for as many as E(s). The authors demonstrate the effectiveness of this approach in section 3. Where they present results on the sensitivity of the solution to changes in kVs and kiv. Here is a combined summary of pages 5 and 6 of the research paper. The authors present a sensitivity analysis and uncertainty quantification framework for point defect kinetics equations using perturbation analysis. The framework captures the response to 50% input changes and can be extended to any finite orders, with convergence criteria implemented to adjust the number of correction terms automatically. The authors apply the perturbation expansion to quantify the aggregated uncertainty due to all input parameters, denoted as K alpha, alpha equals 1, 2, 3, where the deviation from the unperturbed solution from each component is summed as shown in equation 19. The perturbations, ek alpha equals 1, 2, 3, can be viewed as random variables with a given joint distribution. By applying the variance operator on equation 19, the aggregated uncertainty of CV and C can be expressed as a function of the uncertainty of individual input parameters and higher-order correlations. The authors apply this framework to pure alpha Fe under electron irradiation, assuming only point defects are directly produced during irradiation and no defect clustering occurs. They solve equation 1 using the irradiation condition and material parameters shown in Table 1, where dV0 and D0 are the diffusion coefficient prefactors, and EMV and ME are the migration barriers, respectively. The defect sink rate to dislocations is written as equation 20, and the recombination rate is written as equation 21. The solution of equation 1 is shown in Figure 1, which falls into the regime of low-temperature high-sink density scenario. To validate their analysis, the authors consider variations in KIV and KVs, which depend on fundamental defect properties, and introduce uncertainty by considering impurities, local stress, and computation accuracy. They assume an uncertainty range of up to 50% based on Short et al.'s work, where a slight change in vacancy migration energy can cause a significant change in the vacancy concentration profile. The authors translate this variation into rate constants, estimating the change in the vacancy diffusion coefficient given the Arrhenius form. The authors demonstrate the results for variations of KVs and KIV at plus or minus 20% and plus or minus 50% changes, considering independent uncertainty in KIV and KVs. Figures 2 and 3 plot the real and percentage changes in CV and C via direct solving of equation 1, with changed KIV and applying the perturbation analysis up to the third-order correction. The results show that a more negative alpha would lead to higher defect concentration, and vice versa, due to the nonlinear nature of the two coupled equations. The sensitivity analysis and uncertainty quantification on point defect kinetics equations are discussed, focusing on perturbation analysis and vacancy concentrations. Figures 2b and 3b demonstrate the agreement of the third-order correction with the direct solution under various conditions, with higher-order corrections necessary for larger variations. Figure 4 shows the effect of order of correction on accuracy, highlighting a large deviation for the first-order correction but good agreement with the second and third orders. The impact of varying KV on C and CV is shown in Figures 5 and 6, indicating a lessened impact compared to KIV. The analysis also discusses the opposite sign of increment C and increment CV for a given beta, with third-order corrections capable of fully predicting the direct solution. Figures 7 and 8 evaluate the simultaneous variation in both KIV and KV, demonstrating the efficacy of the perturbation methodology for uncertainty in multiple parameters. Here is the combined summary of pages 9 and 10 of the research paper. The authors present a sensitivity analysis and uncertainty quantification on point defect kinetics equations using perturbation analysis. Figure 6 shows the variation of increment CV with time under different perturbation levels, beta equals plus or minus 20% and beta equals plus or minus 50%, and compares the results with the solution from solving equation 1. The dotted lines represent the results up to third-order correction based on equations 7, 8, and 9. The corresponding percentage changes are shown in Figure 6b. Figure 7 illustrates the variation of increment CV, percent, with time under beta equals 20%, comparing the solutions from solving equation 1 and the results up to first-order, second-order, and third-order corrections. The method can be extended to analyze the sensitivity of other rate constants, such as K0 and KISS, in scenarios involving uncertainty in dose rate and interstitial dislocation interactions. The authors conclude that the perturbation expansion method can efficiently analyze the response of point defect kinetics equations to uncertainty and sensitivity in input parameters. The method has the advantage of performing sensitivity analysis on continuously changing parameters by solving a few extra equations, rather than solving the original equation repeatedly. Figure 8 demonstrates the capability of the analyses to generate aggregated uncertainty due to uncertainty in multiple rate constants, specifically KIV and KVs, under changes of both KIV and KVs. Alpha equals 20% and beta equals 20%. The solid lines represent the solution from solving equation 1 with new KIV and KV's values, while the dotted lines represent the prediction from adding the results of KIV-induced change and KIV-induced change. The authors acknowledge the support from the Department of Nuclear Engineering at Penn State University and provide a list of references, including works on radiation materials science, modeling injected interstitial effects, perturbation methods, cluster dynamics modeling, and ab initio studies of helium in alpha Phi.